Hello and welcome to today's screencast. The focus is on part 2 of EPOC, which as you can see here is called slow EPOC. Now before we go into the kind of details and functions behind slow EPOC, it's really important we recap what we looked at in fast EPOC. So if you remember fast EPOC, we focused on that first 3 minutes after exercise and looked at how it allowed us to recover certain physiological components. So if we have a look back at how we finished last lesson or last screencast, it was this. Okay, we looked at after 3 minutes after exercise that we had managed to get our PC and ATP stores resynthesized via endothermic reactions. Second thing we looked at is how we managed to recover our oxyhemoglobin and oxymyoglobin by the 1 to 4 litres of oxygen that we got in the first period, or the first few minutes of our fast EPOC process. Now, what's really important at this point is that we remember that when I first introduced you to the idea of EPOC or recovery, we said that these 4 things were depleted, but we didn't. There were 2 other things that we needed to look at. And if you remember, I also said that glycogen had been depleted massively. Okay, and we'd also had the accumulation or the build-up of this harmful byproduct, lactic acid. Okay, so if fast EPOC helped us recover all of this in the first 3 minutes, our next focus then is looking at how we can replenish our depleted glycogen stores and how we can remove the dangerous byproduct of lactic acid. Now, we do this via slow EPOC. So if I take you back to the next slide, let's have a look exactly how we get this process going. So when we look at slow EPOC, key things for us to consider and to remember. Okay, slow EPOC is going to take, well, it starts working straight away, but it usually takes from up to about an hour up to 24 hours to allow a recovery process. Now, there is something really, really important we have to start with when we're talking about slow EPOC. It takes longer, and because it takes longer, it requires more oxygen. So we need more excess post-exercise oxygen than we do for fast EPOC. So in order for us to understand how we get that oxygen, it's really important we go to the next slide and have a look at how this kind of works together. So, as I said, our key function within slow EPOC is to replenish glycogen, remove lactic acid. In order to do that, we start our study with regard to slow EPOC on the elevation of 2 to 3 rates within our body when we finish exercising. Now, a lot of people would think that, when you stop exercising, a lot of uneducated people, you might say, people who don't study PE as an academic subject, would think that, when you stop exercising, your heart rate's just going to go straight back down. Now, what we have to look at is the idea that when we finish exercising, we still have, in the kind of up to an hour after and longer sometimes, we will still have a high or an elevated heart rate and respiratory rate. Okay, so if we have an elevated heart rate and respiratory rate, this is absolutely vital for us to be able to get in the excess post-exercise oxygen that is required for us to really utilize and I suppose allow slow EPOC to get us to replenish glycogen and to remove lactic acid. So these 2 are absolutely huge. So we're going to study, okay, how these 2 allow us to take the oxygen in and remove any waste products that we don't want. On top of that, we're going to have a look at how body temperature also remains elevated and helps the process of slow EPOC, and then we'll come back to have a look at how, by elevating our heart rate and respiratory rate, we can use the excess oxygen we get from here to allow us to remove lactic acid and to replenish our glycogen stores. So that's the process. Part 1, we're going to have a look at this. Once we have an understanding of how these start the process of slow EPOC, we'll then have a look at how the excess oxygen from here allows this to be recovered and this to be removed. Okay, so part 1 then. So this is our focus, as I've said before. We keep coming back to this. Remove lactic acid, replenish glycogen. Let's have a look though at our first point. Now, 5 to 8 litres of oxygen for slow EPOC. Okay, so let's have a look at how we do that by maintaining an elevated respiratory and heart rate or circulatory rate. So, slow EPOC, we have an elevated respiratory and heart rate. This is where your notes need to be really good now. Okay, so let's have a look at how having an elevated respiratory and heart rate will aid our recovery. Okay, so it does it. Firstly, it aids our recovery because more oxygen is required. Now, specifically, how do we do that? Because our respiratory rate is increased, we breathe more often in recovery. It maintains its elevation, or it maintains a high level. It allows 5 to 8 litres of oxygen to be transported to the muscles. Okay, and on top of that, by getting the oxygen in, it also, because our heart rate and respiratory rate are elevated, it also allows us to get rid or remove the things we don't want. So it allows us to remove carbon dioxide and lactic acid, those two byproducts that we do not want. Okay, so we can remove that via the blood, okay, and then we can exhale it out via our respiratory rate. Okay, so that is how that first process works. So hopefully you can see how important it is that, that we see that by having an elevated respiratory rate, this allows us to get in the more oxygen, specifically 5 to 8 litres of oxygen we're going to need when we move on to part 2 of slow EPOC. Okay, so what else remains elevated? As you'll remember from the previous slide, we also, when we finish exercise, our body temperature doesn't just plummet back down to rest. Okay, it takes a while, so it maintains elevation. Okay, it doesn't go straight back to resting levels. And the reason why we have an elevated body temperature is because it increases our metabolic rate, and this is how it helps slow EPOC. So what that means is it means we can continue to break down fats to produce energy to aid our recovery. So if we consider that from there, our body temperature remaining elevated allows us to gives us an increased metabolic rate, so we can metabolize the fuels that we need to create energy to help us with our the process of slow EPOC. Okay, so if I was going to say on this, that's what you need to know with that. Hopefully that makes sense. We know that fats is our key energy, or the biggest energy store, so if we have that metabolic rate being high, we can break it down better. Okay, so that will help our recovery here. Now what I'm going to do now, that's our first thing. The whole of slow EPOC needs to start from this point. Okay, now what I will say to you really is the most important part of this, of course, is the fact that we've got 5 to 8 litres of oxygen. Okay, so we've got this in via the elevated respiratory and heart rate. Okay, so now what we're going to have a look at is the next stage. So that's our start point, nice and easy. When we're in recovery, our slow EPOC really is, I suppose, emphasized or helped by the fact we've got these elevated rates. So if we go on to here then, if we're remembering our key focus within slow EPOC is to remove lactic acid and to replenish glycogen stores, what we need to do now, and I think this is really important, I'm going to go back slightly there. Now, if you consider we need to remove lactic acid and replenish glycogen stores, I think it's really useful to just have a quick thought and think, right, if the process or the function of slow EPOC is to replenish our glycogen stores and remove lactic acid, we need to remind ourselves of, during exercise, the process that allowed our glycogen to become depleted in the first place, and secondly, the process that allowed lactic acid to accumulate. So we just remind ourselves that within the glycolytic system, when we were working at high intensities from 10 seconds up to 3 minutes, if you remember the process, it went like this. And I don't need you to make notes on this. This is really just to show you how glycogen got depleted in the first place. So remember that glycogen got broken down or depleted into glucose. Glucose got then broken down as well. So if your glycogen has gone, your glucose has gone, and it's converted into pyruvic acid. If you remember that we had no oxygen present here. Now, because there was no oxygen present here, this meant that LDH, if you remember, converted pyruvic acid into lactic acid, which caused us problems. It led to obla, etc., fatigue, all of that stuff. So if you remember now, this should remind you, don't need this for the lesson. I just thought it's quite nice to visualize the fact, if we're trying to replenish glycogen stores and remove lactic acid, how did they get there in the first place? Well, it was by this process that you've studied before. So what we need to do now then is have an understanding, if this was the process that led to us having lactic acid and depleting our glycogen and glucose stores, how do we get it back? how do we use slow EPOC to get lactic acid removed and to replenish our glycogen stores? And I'm going to show you that now. So the key question for us, and this is where you've got a choice here. This is an optional slide. What I want to show you now is visually the process, that how we use the 5 to 8 litres, the extra oxygen, the 5 to 8 litres that we got from having an elevated respiratory rate and an elevated heart rate. Okay, so how we use the oxygen to actually allow us to remove lactic acid and to replenish glycogen. So you don't have to make notes on this. You can just watch it. There will be a slide after this that will allow you to make notes. So we have a look now. A lactic acid is accumulated. Okay, so when we are in recovery and slow EPOC, because we've had that elevated heart rate and respiratory, we get the 5 to 8 litres of oxygen we need. Now, as soon as that comes into a body, we can start to use it. Usually, remember, from 3 minutes upwards, around an hour. When we start to use that, this is how it works. The excess oxygen used in slow EPOC basically works in the following ways. It oxidizes or converts lactic acid back into pyruvic acid. So if we use that term there, the extra 5 to 8 litres of oxygen oxidizes lactic acid into pyruvic acid. Okay, so once we get lactic acid oxidized back into pyruvic acid is absolutely vital with regard to carrying out the functions of slow EPOC, removing lactic acid and replenishing glycogen. So when we've converted or oxidized lactic acid back into pyruvic acid using the oxygen, obviously, it then works in 3 key ways. So pyruvic acid is converted in 3 ways to allow us to finish our recovery process. The first way that pyruvic acid is converted is responsible, it's actually responsible for 60%, okay? So 60% of pyruvic acid is converted or oxidized, we can use, into the Krebs cycle in the aerobic system, which you'll remember. And when that pyruvic acid is oxidized into the Krebs cycle, it allows us to remove carbon dioxide, and it provides us with energy. Now, we don't need to talk about ATP in this case, we just need to say it provides us with the energy we need to help our recovery process. So, lactic acid oxidized into pyruvic acid. Pyruvic acid is then removed or converted in 3 ways. 60% of it oxidized into the Krebs cycle, which allows us to respire aerobically. It removes CO2 and it provides energy. Now, the next conversion refers to 30% of pyruvic acid. So 30% of pyruvic acid is then converted back into glycogen and glucose via 2 processes: gluconeogenesis for glucose, glyconeogenesis for glycogen. And this allows us now to replenish our glycogen in the muscle and liver, and it also allows us to kind of restore the glucose or the blood in our blood. Okay, so 60% of pyruvic acid oxidized into the Krebs cycle, 30% into glycogen and glucose via those 2 processes, which I'll put on the next slide. And the final way that pyruvic acid is converted, and it refers to the final 10%. So 10% of pyruvic acid is converted into protein, and it's removed via sweat. You could add it, or if you're not making notes, sweat and urine, which will be on the next slide. So I thought it's quite useful to see that, on the previous slide I showed you how glycogen went down and then into lactic acid. Now we're looking at the opposite way. Because oxygen is present now, a different set of events happens. So the lactic acid is oxidized to pyruvic acid, which is oxidized again into the Krebs cycle for 60%. And you can see how that happens in a visual kind of system. So you did not need to make notes on that. And what I will do now is put this onto a slide where you can make all of the notes that you're going to need with regard to answering an exam question on slow EPOC. Okay, so what we do now then. So first things first, so back on, always the same. So let's start in here. So what is removed and replenished during slow EPOC? Now you probably feel like you could answer this without me going through it. So what is removed? We should know that lactic acid is removed, and we should also know that glycogen is replenished. Now what we need to do now is know how it happens. Now I think that's really, really useful. If we have our start point as lactic acid, that will allow us then to think, right, we know what happens. But before we talk about that, we need to talk about the oxygen, because without the specific I suppose, litres of oxygen, we really won't get credit in the exam for what we know. So 5 to 8 litres of oxygen are used to convert lactic acid back into pyruvic acid. Okay, and once we know that, we've then got to say why, we've got to say how. Pyruvic acid is then converted in 3 ways at 3 percentages in order to allow our body to recover. So 60% of pyruvic acid is oxidized into the Krebs cycle. 30% of pyruvic acid replenishes glycogen in the muscles and liver, and then glucose in the blood. Okay, the things in brackets, glyconeogenesis or gluconeogenesis, are optional. They are just the process behind the replenishing of glycogen and glucose. You don't want to put them. You're not going to get marked down for not using them. And the third way pyruvic acid is converted is 10% of it is converted into protein and released as sweat or urine. Okay, so that is our process. Now, in terms of how long it takes, you should remember from the first slide that when we're talking about the process of slow EPOC, it will take place. And I'm going to ask you to change this. I mean, it starts working pretty much at 0 minutes, but 3 minutes it takes over completely. But it will take, if we change that to an hour, up to 24 hours. Okay, so 3 minutes to 24 hours would be fine, but it usually takes somewhere between an hour and then up to 24 hours. Okay, it starts working straight after we finished our fast EPOC. So if that is our process, that's the physiology then behind the process of slow EPOC. What we need to do next then is just to finish this off, is just to remind ourselves. So at the end of slow EPOC, if I go back to the bar graph, what would it look like? Okay, so if you have a look now, if we look at what our physiological measurements would be like 24 hours after exercise, you would see here our heart rate and respiratory rate would now be low. Okay, because 24 hours after exercise, they would have dropped right down because our body would have recovered. On the flip side to that, because all of the processes have happened, glycogen now would be back up. Okay, so glycogen would be replenished, glucose would be replenished as a product of that, and then on top of that we would now have a low level of lactic acid because we've removed it. And obviously what we need to remember is that by having these situations that during slow EPOC allowed us to get this back, to remove that, and the whole process that we went through. So bearing in mind, you need to make sure then that you can, I suppose, really explain what the function of this being high was in the first place, what the function of that was being high, and then now they've dropped. That's because we've got our glycogen back and our lactic acid removed. Okay, so that's your key notes. Please make really good notes on this. And the main process is that we knew that these were high, this was high, why. Once we know these two were high and why, then we need to look at the process behind how this got the extra oxygen in to allow us to convert this back to pyruvic acid. And then once we converted it back to pyruvic acid, we could then go with a process of the 3 ways that pyruvic acid was reconverted or converted or broken down in order to allow us to get our glycogen back, to oxidize into the Krebs cycle, and finally to convert pyruvic acid into protein to allow us to sweat out or urinate out any excess product. Okay, thanks very much.